simulation and experimental parameters are there. This is the grid voltage and frequency, battery voltage, battery capacity type, and the, passive components and the solar PV parameters. And are the hardware components are there. And here again, charging 800 watt is taken as the reference charging power. And battery, again, our objective is to grid voltage and grid current are in the same phase with the same shape, with the power factor is unity. And this is the capacitor voltage, which is in the middle of the converter. This is also known as the coupling capacitor voltage and inductor current. And this is the switch voltage. And it is this result is during the propulsion operation. Again, propulsion operation is by varying the uh, load power. And this is the regenerative braking operation. In regenerative braking operation, battery is charged through the regenerated energy. So now I will come to the another different types of the onboard charging solution, which is used in the electric vehicle. Uh, it is the during the charging, as we know that during charging, uh, the converter which is used for the propulsion operations is not utilized. So as we know that machine, there are electric machines are there, in that there will be windings. So during the charging, machine winding can be used as a we can see this diagram. Machine winding can be used as the energy storage element. A three-phase inverter, that is a DC to AC converter. DC to AC converter can be used as uh, uh, a operates as a boost converter, or it can be boost converter. So this concept is widely used in the electric vehicle for the charging application, so that completely the independent charging converter can be reduced. So this is the block diagram of electric EV architecture through the machine winding. So uh, we can see this table. What can be the power we can go during the charging when we are utilizing the machine winding? Because the motor which is uh, used in the electric vehicle, depending upon the type of electric vehicle, here for the some models the motor rating is given. Nissan ENV 280 kilowatt, Tesla Model S3 250 kilowatt, and like that. From the induction motor based based EV model. And in case of PMSM based uh, electric vehicle, so power can we can see the motor rating 160 kilowatt for Nissan Leaf E Plus, Chevy Volt for 149 kilowatt. So such a high power motor, and according to that there will be inverters also selected, DC to AC converter. So these motor winding and inverter are utilized during the charging operation. So first configuration I will show here through some a mechanical switch or on off switch required. We can see this configuration. So switch K2 and K2 dash is closed during the charging operation, and K1 is open. So we can see, we will connect a single phase grid. In this is the DC to AC converter, which is DC to AC converter, which now it will act as a rectifier during the charging. So so two leg we can use two leg of the this when it is closed, so these two leg can act as a boost converter. Okay, through the boost converter, and it will be a boost. It will automatically, it will do the, as a, we know that boost PFC, it act as a boost PFC, and will uh, charge the battery. There may be a chance that in DC link battery there will be a DC to DC converters also there. If it is not utilized as a means, if this circuit in a propulsion operation, then these motor winding in during the charging, these motor windings will be act as energy storage, and during propulsion operation, whatever the motor windings generate the revolving flux in the machine, so this switch will be closed and K2 and K2 dash will be open. So this is if there are a two motor system, as we know that in different types of EV configuration, there may be it's maybe one motors or two motor, or even sometimes a four wheel has a four different motors are there. So if it is a two wheel system, sorry, two motor drive system, so AC supply can be connected between the neutral point of the converter. Okay, neutral point of both in this AC supply can be connected, and this both converters act uh, as a boost PFC. So this is a integrated onboard charger utilizing machine winding in the charging circuit. Again, another type of configuration. Here we are seeing that a single phase diode rectifier is used to connect the single phase grid. So uh, we can see here uh, these this is the rectifier, and this will act as a two phase interleaved. Here it will be used as a interleaved converter. If rectifier is there, then directly it will act as a two phase interleaved system. As there is a one so which is mandatorily we have to fix it, because it is a motor winding. In motor winding there will be a, when current is flowing, so there will be a torque production also there. So if there will be a torque production will be there during the charging, motor may they kind of a hunting or some kind of oscillations may take place. So uh, as we know that this is the standard torque equation in the PMSM. I'm taking this in a PMSM machine. So this so torque, finally the torque generated is this expression is comes. So theta is the cos. This theta is the electrical degree in electrical degree. So if theta E equal to 90 degree, so torque production will be zero. Electromagnetic torque, which is sometimes it is known as the charging torque, will be zero. So motor rotor position from the reference axis should be in a such way that it maintains. We have to ensure that it will be at a 90 degree, and after that we can lock the motor in any means, so that there should not be any charging torque. So whatever the previous in a previous slide I have shown, it is and same thing, same type of converter is there, only at a grid input side where the three phase grid is used. Three phase. This is the buck type rectifier. Buck type rectifier is this one. So this only increase the power level, because as we know that motor has a very high ratings in the electric vehicle. So if you want to increase the onboard charging powers, because we cannot we cannot increase the charging power through the single phase system, because single phase has its limitation. We can draw a maximum, as we know, all know that a 16 ampere current from the maximum which is available in every household power switch. So maximum 16 into 240, so around 3.2 3.3 kilowatt we can take from the single phase supply. So if you want to increase the power, so we have to go through the, we need to connect a three phase supply through the three phase AC/DC converter. Again, it will be act as a two phase interleaved DC/DC converter. So the last slide, last two converter which was discussed uh, was the grid-based charging of utilizing the machine winding in on-board application. This is the on-board application solar PV-based charging system. It is here a DC to AC converter which is used in the charging circuit utilized at the three-phase interleaved buck converter. This is the arrangement here. Solar PV is connected at a DC link, and machine winding here as the require in these all the three, including this converter, we have seen that all these three converters converter for the onboard charging require the neutral point assessment. This is the one point. On the basis of that, we compare the different topologies for the onboard charging application. Because if it is required, because I'm connecting a diode, neutral point and battery to uh, because battery, we can see here battery is connected a DC link during the propulsion operation through this bidirectional switch, so that there should not be any connection between battery and neutral point. So this diode is required. Even in any in neutral point, voltage is always zero, battery voltage is a positive. So even in unbalanced situation, the voltage will not generate as much high compared to the battery voltage. So this diode will be reverse bias anyway. So this is the operation of three-phase interleaved buck converter through the solar PV charging. And operation have been shown, but I will not discuss in detail interleaved operation, because here the arrangement and the way it is used, that is more important. And so interleaved, all these three switches operated in a PWM. So in PWM means they will have a phase shift of 120 degree of each switch. So also zero current switching also implemented in particular converter. So this is the ZCS arrangement, and we will see ZCS operation all these in during in the result section. Okay, so in a result we can see here solar PV solar irradiance is varied, solar irradiance is varied, and here the ZCS operation has been shown. Switch for the switch S1 and S3 I have shown here at the uh, at the when PWM is here, PWM is going to zero. So current through the switch SA1, sorry, S1 is going to zero. So this ensures the zero current switching operation of the converter. So this is a switch voltage across the switch S1. And one important which we have analyzed that through the zero current switching and compared to hard switching, there is a efficiency improvement around approximately 2%. So again, using the same concept, inter this DC to AC converter and motor winding used as during the charging. There was a solar PV based charging system. Now it is the grid based charging system. Okay, it is a grid based uh, charging. So a front end AC/DC converter used. So this is the only arrangement as I control techniques for the AC/DC converter. This is the DQ control. It is the standard DQ control techniques of AC/DC converter, where VDC is taken as a reference. It generates ID current, a direct axis current, and then a direct axis voltage is generated. Similarly, VQ is generated, and from DQ to ABC, a reference voltage is generated for the generation of the switching pulse for the 6.
You're not audible. Ankit sir? Am I audible, Ankit sir?
Hello.
Yes, sir, you're audible.
Okay.
Lights are not shown.
Okay. It is screen is visible.
No, sir.
It is not visual.
No, just now it finished. Please share it again.
Okay. Yes. Now it is visible.
Yes, sir. Fine.
Okay. Thank you. So control of three-phase interloop DC-DC converter. It is a conventional one. These PWM pulses, which is for the three switches S7, S9, and S11. This is the which is connected lower at a lower side. So these are 120-degree phase shift between these in the PWM of the switches. So now it is some real-time experimental real-time results are there. For this, it is validated in OpenRT 4512. So this is the grid voltage and grid current. Again, for whether when we are going to charge, the first requirement is to the grid side power quality should be maintained, and this is the three-phase in three inductors currents. Three inductor currents are there. So again here ZCS concept again is implemented in here, and which is achieved well. So and here the losses in the different system is shown. It is important. Here we can see that uh, semiconductor loss in interfacing converter means AC/DC converter. Same means in the switches, a semiconductor loss in the propulsion converter. converter, which is DC to AC converter, which is act as interleaved converters, is around 14%. Filter and inductor loss are there. So these are the losses, complete loss breakdown in the system. And again, a dynamic operation of the converter is tested. We can say through the dynamic operation, it is the grid voltage. Only here I have shown the grid current, grid current. So grid current are again in sinusoidal shape and through the variation in the load power. So it is according to that grid power is changing, variation in the grid load voltage. So efficiency maximum, because here efficiency is it is analytical calculation. So around maximum it is going 91%. Maybe in practical and more practical way, it may reduce to 88 or 89%. It is completely analytical. So till now I have shown the charging solution through the machine winding, where either through the grid or through the solar PV. So this is the first converter system where charging is shown through the AC/DC and DC/DC AC/DC charging and DC charging both. So DC may be, it may be any kind of DC. Okay, so it is supplied through the motor winding and DC to AC converter and three-phase AC/DC converter, which is here, and the battery is connected to a bi-directional buck boost converter. Okay, so when this concept comes, uh, power level in the onboard charging can increase in tremendous way, because if we use a three onboard charger has a uh, onboard charging for the three-phase grid, uh, we can we cannot increase the power much through the on if we connect a three-phase system and AC/DC converter. So if there is a, because if we want to increase the grid power charging power through the grid, so according to that a additional converter in that, if rating should be again according to the charging power level. So we are placing it in the inside the vehicle, so we cannot increase its power rating of this converter. And this particular converter, this DC to AC converter and machine winding, which is its power rating is designed based upon the propulsion system, so it is already there in inside the vehicle. So through the DC power supply, we can generate the very high power at the level of the motor and inverter rating. So if DC will be there, so on board on these means both AC and DC will be, so on board charging power may increase in the very high, it may reach to 100 kilowatt or even more. So we can see the parameters here. Type 2 on board AC charger, because in three-phase system comes into the level 2 or type 2. So it is limited to, again, type 2, we can say in onboard application it is around 19.4 kilowatt. In some standards it may reach to 22 kilowatts. And through the DC supply, we can see here drive 10 inverter act as interleaved DC-DC converter, and motor and drive power rating, whatever rating is the 100 kilowatt. So and DC link voltage 600 volt, and but these are the battery rating. So here we can see grid is supplying 19.4 kilowatt, and DC power, which is varied according to the motor rating. Till here they have taken 90 kilowatt from the DC supply. So overall 90 plus 19.4. So that much power is maximum charging power in a onboard application when we utilize the DC any DC power in the charging system. So this is a another AC/DC charging approach using the machine winding in electric vehicle where some different arrangement is used. Here again, uh, uh, this is the solar PV system. Okay, this is the solar PV system which act as a two-phase and utilizing this converter as a two-phase interleaved. And this is a, buck type rectifier. Okay, this is the buck type rectifier, which is grid is connected through this converter, or it is sometimes it is also known as the interfacing converter. Sorry. So here a control aspects has been shown of this AC AC DC converter. So hysteresis control techniques has been used. We are taking the reference power whatever the in a very first converter in second converter I have shown in onboard charging application at the beginning of the slide. So solar PV is charging the battery. If whatever the reference charging power, we subtract it from the reference power, and rest of the power is supplied from the grid. And this is the error signal which is generated here from the reference grid current and reference measured grid current. This is the uh, these are the error signal, and there will be a threshold which of the hysteresis control, and based upon that switching pattern has been means generated for the three-phase AC/DC converter. So we can see here operation is a simple one, and when uh, any uh, when upper and lower switches are turned on, so inductor will store the energy. When all the lower switches or all the upper switches is turned on, inductor will dissipate its energy to the battery, this diode. This is the a fundamental concepts of this buck type converter. So from the solar PV, it will act as a two-phase interleaved converter. Okay, two-phase interleaved converter. Interleaved boost is we have to keep in mind. It is here it operates as a two-phase interleaved boost converter. Phase interleaved boost converter. These are the parameters. Again, here uh, 19 kilowatt from the grid, 101 kilowatt from the, it is design that from the solar PV, because they and total reference charging power is for this is 120 kilowatt. So we can see here some along with some dynamic analysis. If 110 kilowatt reference power, so then 9 kilowatt is generated from the uh, grid, and 101 kilowatt we are assuming that is for at 1000 solar irradiance their power is generated 101 kilowatt. So total reference power is 120 kilowatt is met. If we are increase the reference power, so then grid will supply all the its power, means all its power means what are the uh, limit of the type 2 AC charging. So during the dynamic operations, this is the battery voltage, battery current, and battery power. This is the solar PV power variation with a different solar irradiance. We can see at 1000 solar radiance power is generated 101 kilowatt, and at 200 solar radiance it is around 19.27 kilowatt. This is the battery voltage, battery current, and battery power. Battery power and SOC variation. So here we can see if grid is used during the charging operation. Okay, so only grid is available. If a grid is not available, so the solar supply only the power. Okay, so some here we can say grid and solar both when we are using. So if only solar PV is used, then grid power will be 0. Okay, if we are changing the this is the real-time waveform. So grid power is 9 kilowatt. So reference power is 110 kilowatt, and like that. This is the if reference power is increased to 120 kilowatt, so grid power will increase. Okay. This is the solar variations in real time, and according to that, solar irradiance variation and solar power variations are there. And this is the reference power variations. And after that, what is the battery current, battery voltage, and battery power. Now I will come to the some multi-phase how the multi-phase system or multi-phase machine used in the charging. If a drive system based upon the multi-phase system, so we are bound to use it as a uh, multi-phase charging also there. So multi-phase machine, when it is used in a charging, whether it will be used as a three phase or a single phase, not a multi-phase charging. I said wrong. So multi-phase means here we can say three-phase grid. Three-phase grid is you connected a five-phase machine through the arrangement. Phase A is connected to the means this at terminal A, and phase B is connected to the winding B and E, we can see here, and phase C of the grid is connected to the here and here. So it is the uh, this arrangement. Okay, so during charging, switch S1 S2 will be open. Okay, during charging, if it is propulsion, then S1 S2 will be closed for the five phase operation. Okay, so when we look in an equivalent circuit here, we can see here the three phase supplies there. These are the inductors are parallel some between B and E, C and D. So, and this inductor, five phase machines inductor, winding inductors, and this five phase inverter, which is five legs are there, and equivalently used as a three phase grid system. Okay, here some switches we have to think about. We have two switches simultaneously operated, two switches. Phase A connected to this, so phase this switch. Okay, so it will on, and its body diode, it will act as a boost PFC, and phase B and other point B means connected here, and E is connected here. So these switches operated with the same PWM. same PWM, they will store the energy and they will dissipate energy, stored energy inductor to the battery, in battery to the upper switches body diode. Okay. So again, this is the six phase. If a machine is the if six phase is used, so six phase the here the through nine switch converters are there, nine switch arrangement during the charging. During the charging, uh, S1 S1 this switch will be open. Okay, so grid is connected to the switches, and equivalently we have seen in this during the charging these switches will be turned on permanently, these switches, and we can see here equivalent diagram. Okay, so switches had been these switches turned on permanently, and again it will act as a boost PFC converter. For the phase A, this switch will be operated in PWM. For phase B, this one. For phase C, this switch. Okay. So these are the arrangement for the charging through the six-phase machine. So another one is the there nine-phase systems are there. Nine-phase machines will be there. So in nine-phase system, there are both possibilities are there. Uh, in neutral points, we connect the supply. It can be act as a single phase grid. We can utilize it as a single phase or even a three-phase system depending upon the requirement. So I will show the equivalent diagram. Uh, okay, so again, what I told, whatever is the machine is there, machine nine phase, six phase. So we charging always through the three phase or a single phase charging. So these converters become equivalent to three phase means three phase DC to AC converter. If if you want to have a single phase supply, so between two neutrals of the supply, there will be during two neutrals there will be a single phase supply and one neutral point left open. Okay, so this is the another onboard charging solution between vehicle to vehicle. So because as we do in one vehicle, there will be a battery and another vehicle will be another battery. So through this particular connection, uh, we can transfer energy from one vehicle to another vehicle. So depending upon the battery voltage condition, we can operate this converter as sometimes as a buck converter or a boost converter by let's say in this configuration, switch S1 will be operated in a PWM mode, uh, and and it will transfer this inductor, we will combine it and transfer the energy to the uh, battery. And when this switch S1 will be off, we can see here a body diode of this switch S2 will circulate the stored energy in inductor to the battery. This is the conventional buck converter operation. So now I will come to the charging scenario when reverse boost operation. Again, in a reverse boost operation, switch has to be operated in a PWM mode, and when switch S2 is off, it will transfer its energy to the battery from VB2 to VB1. So now I will show one work related to the for the application of a solar PV in electric boat. So this is the our work which we have uh, published for the if solar PV assisted electric boat is there. So what are the different things? First, when we think about when solar PV based electric vehicle and solar PV based, let's say, I'm talking about the onboard application, solar PV based electric boat. As we know that except some light electric vehicle, most of the time solar PV cannot be installed on the roof of the vehicle. It will be because the space is not that much. But in case of uh, solar boat, there will be at its roof because it's a big size. Its roof may be designed in such a way that it can generate a lot of power. At an onboard application. So if completely it is on a solar based electric boat, so we have to design the solar PV uh, power solar PV modules so that required amount of power can be generated. Okay, so in this, one important thing is that this particular converter is operated in different modes. This is the three-port converter. Three-port is one port at PV. Second, at the second port there is battery, and third port is the load. Whatever load it may be DC link, and after that motor and the drive system will be there. So in that different situations come, and I will show these are the operating modes when battery to CISO mode. CISO mode, single input, single out. Battery is supplying power to the load. In that situation, I'm assuming that PV is not present, and all the power which is met to the load is supplied by the battery. Okay, so and then second is the DSO, dual input, single output. Single output means the load is the output, and PV and battery act as a input. Okay, so in this situation arise when load power is higher than the whatever the PV is generating the power, because if PV is generating power, there may be chance PV supply all the power to the load. Okay, so PV can supply power if load is load power is higher than PV, then battery and solar PV both supplying power to the load. Pseudo mode is the single input dual output. There may be a situation that load PV is generating more power than a load. This is the important mode of operation in context to the solar boat. Okay, because when solar is at the rooftop of the solar is the rooftop of the boat, so it is again power, maybe it is generating higher maybe some than the load power. So solar should converter system we should design in a such way that, and our control aspect is such that it can bypass the excess power to the battery and some power to the load directly. Okay, so this is the very important move, and this is the not a case in the we usually not discuss in the electric vehicle, because except what I have told, some light electric vehicle e-rickshaw, sometimes we are now these days we are seeing that there will be a rooftop solar PVs there. So these are the different modes of operation which we have seen in table. So operation is this converter is, as we if you look very in attentively, so we can that this converter is derived from the again SEPIC and boost. boost operation and SEPIC operation will be take place in a different mode of operation. Okay, so during the CISO, it is a battery is supplying power to the load. It is a SEPIC operation. And here one thing, here boost MPPT is connected and the input is here. Solar output is here. Okay. So this is the pseudo mode, means a single input, dual output, whatever we have seen, that a single input dual output case will come when the solar PV is supplying power to the battery and load both, because when it is supplying act as a when it is supplying to the battery, so this operation will be in a boost. Okay, so switch S1 will be on and battery will take the energy in when switch S1 will be off. If it is, and also there is a possibility that solar is supplying power to the load also in and in this mode of operation, the converter act as a boost when solar is supplying power to the load, and if it is supplying power to the battery, it will act as a uh, boost operation. So DSO mode is there. DSO mode is the very simple, in that both solar PV and battery is supplying power to the load. Even there is a situation, P load is greater than PPV. Okay, P load is greater than PPV. So this is the simulation result of this particular converter. So for this year, 500 for this 500 watt is taken as a reference power. So in a CISO mode, if solar is not generating any power, battery is supplying all the power. Okay, so SOC of the battery is decreasing. When in a DSO mode, dual input, single output, solar is started generating power, but it is not, it is less than the load power requirement. Again, then it means battery and solar both are supplying. If let's say the solar is exactly supplying power, whatever the load requirement, so these load requirements, so battery will not charge or discharge. Its SOC will be constant. If solar is generating more power than load power, so battery will charge. If at this point, if battery is fully charged, then solar will not operate in MPPT mode, because battery is fully charged and load power is also less and solar is generating high. So without MPPT, it will operate. Okay. So this is all about from my side. If you have any question, you can ask. Hello. Hello. If audience, if participants, if you have any question, you may ask.
Hello. Are you there? Hello.
Hello.
Sir, your voice is not
Okay, okay.
audible.
So, if you have any question uh, that we can take here, as well as if you have some, if you want to some, because some more discussion, if you want to particular converter, I can discuss here.
Sir, one question from my side.
Hmm.
Sir, may I ask?
Yes, yes.
Sir, what is the effect of chattering in battery charging? Chattering,
Jetri.
or we can say ripple current
Yes,
ripple.
yes, 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 yes. Okay. Uh, Ripple current, as we know that from the fundamental point of view, uh, we can see uh, if there will be a ripple in the battery current, let's say it is high frequency or low frequency ripple, so it's a RMS value, as we know that the waveforms will increase. At that, one thing is that RMS value will increase, then definitely the current I square R losses in the internal resistance will increase. And as we know that this I square R losses leads to the temperature rise. Okay, so at the temperature rise will affect the battery cycle life. One aspect, and we, if you want to means in some converters there will be a high ripple at the output side, depending upon the situation converter. So if you still we want to suppress the uh, ripple, so filter size will increase. Okay, filter size will increase, so filter size will be it's increase the weight as well as the cost of the system. Okay, so battery cost and battery sorry, total charging cost will increase, and overall charger size may increase. And there is one thing I will show here in just wait.
There are few more questions in chat box as well. So,
Eh,
sir, you can read and answer them.
Yes, you can see here in this particular converter operation when it is charging from the grid. Okay, this just wait, from the grid. So this is the single stage charging system, single stage in single phase, single stage charging. As we know that when we derived the multiply VB IB power balance V phase I phase cos theta. So IB current has a function of cos 2 omega t. So cos 2 omega t we can see in the result here. A battery has a second harmonic second harmonic or low frequency ripple. This is the twice of the, we can say this is the 50 hertz. Okay, so twice of the 50 hertz means 100 hertz ripple is coming in this configuration. If it is a single stage, if we want to filter out it, one I either we add a filter, inductive filter at the battery terminal, or one more stage means from the this after that but after this point there will be another uh, DC to DC converter. Okay, so to reduce this ripple, and this ripple will affects definitely life of the battery, so depending upon the charger design and battery also, because as we know that lead acid battery has a capability, it is rugged, and it can take high ripple, but a lithium ion battery cannot used for very high ripple, means where the ripple is large. So mandatorily either we have to use such kind of ripple arrangement. If there, I have shown here through the simulations, and I have not added much filter requirement. If you increasing the filter, so definitely this ripple will reduced in a single phase system also. So, but what I have told earlier, the either charger weight and overall cost will reduce. But we can see in case of if it is a three-phase charging system, in three-phase charging system, as we know that there will be no pulsating power is there, so there will be no pulsating current at the output even in a single stage system through the power balance theorem if we apply. Okay, so this is the point we have to keep in our mind, and this is which is shown in all the single phase single stage system. Okay, so if and we use the single stage system because if when we talk about the onboard application, so it is important that charger size and weight we focus on light. So people prefer the uh, single stage system. So in a compromised way, because we can increase filter in some extent, so that it should not increase much ripple. Otherwise, what just wait. If this uh, in this particular, I will just erase the things, then again show you. If there will be no ripple, so if it is a grid based charging, so battery current will vary in this fashion. If this is the T, this is the IV. अब यहाँ पे ये मैटर करता है कि अब आप कितना इंडक्टिव एलिमेंट और फिल्टर एलिमेंट ऐड करते हैं, अकॉर्डिंग टू दैट it will reduce, ripple will reduce. Okay, so it's means if we there is a lead acid battery, so we have to not much means lead acid battery has what I've told some rugged behavior, so ripple it can absorb the high low frequency ripple, but in case of lithium ion battery, so we have to take care about it. Okay, so this is the in all the single stage single phase system. If what we have shown in a three phase charging, uh, I will come to the three phase charging. Here not, it is also a single phase only. In this I will coming, there is a one converter. So here a three phase charging system is there, but it is here automatically two stage. So means low frequency ripple will definitely removed. Another converter was there, which I will show. This one, yes. Here the battery is connected at the in a single stage, but it is the three phase supplies are there, so no single means the low frequency ripple will appear. I will show we can see this is the not a low frequency ripple, this is the high frequency ripple, this we are seeing. So there is a no low frequency ripple in this particular configuration, even in the it is a single stage system is there. So in case of the three phase. Okay, so in here, but it is when it is combined both, means it is the this battery current is there, but it is the yes, solar PV, and again it shows that when both operating are simultaneously, so battery current has only high frequency ripples is there in a three phase. And similarly, in case of even higher phase system, as we know that in higher phase, why we use the higher phase system, uh, higher phases in the electric drive, because the torque ripple is reduces in the multi-phase machine system as we increase the number of phases. Okay, so torque ripple reduction and number of, and another way, because some electric drive or electric vehicle is a kind of a specific thing where we do means anyway we don't want to stop it because when number of phases is increasing, its fault tolerant capability is also increasing. Okay, so fault tolerant capability means if reduced number of phases, our drive we can run. So this is the another reason why you use we use the multi-phase system in different configuration and different onboard charging configuration. If but this multi-phase system is not designed for the these multi-phase machine is not designed for the charging point of view, it is completely from the propulsion point of view. Okay, and one important thing is that we use the multi-phase, some multi-phase system has a very another important thing we can see here. uh, this one, this 9-phase system is there. So we means if we want to, this is the arrangement, if we want to use it as a three phase, only three phase, so there will be not a requirement of any mechanical type of switch. Okay, so another which is inherently it comes in this 9-phase system, we just see it. If we want to add only three phase charging, so there will be no mechanical switch requirement, because this is the another important because the winding configuration and reconfiguration take place. Okay, so configuration and reconfiguration take place, so these mechanical switches are required, but in this particular 9-phase system we can see here that we don't require any if we only use the this three phase uh, charging. Okay, so we are, yeah, and even if let's say we are using only single phase, this complete single phase, so only in between the neutral point, this is the also one when we compare the different topologies or different converter configurations in the electric vehicle onboard charging. So neutral point assessment is another parameters also, because here we are connecting either in a three-phase system or in a single phase system. So we are assessing the neutral point also. So a neutral point assessment or it should be available for the connection of the grid supply during the charging. So in I will show some topology don't require neutral point assessment. If you remember in very first in first slide of the when machine winding used in the charging circuit, I will show. Look it here. This particular configuration, this topology will be best in many way, because we are not assessing the neutral point. We are not utilizing any uh, mechanical switch also, or on off switch. Here I'm talking about only which is not operating in PWM, on off type switch. Okay, it may be mechanical or it may be now these days there is no I'm telling a mechanical switch, maybe cost is less. Even we can use a semiconductor switch as a on off. Okay, so that is not used in this particular configuration. So otherwise, if you beginning of the this particular charging system, if anyone use later on for the this motor and DC to AC converter in charging circuit, so its neutral point should be available. But in this particular configuration, it doesn't require. And so in this this configuration, which is a three-phase charging, again in this converter system, we don't require the neutral point assessment. Okay, so these topologies are compared in these parameters also. What are the mechanical switches are there, are the neutral point assessments are there or not. So we have to keep in mind means while using such kind of topologies. So if you look in most of the cases, uh, we use the neutral point assessment. We whatever we I have discussed in this topology, what again DC supply is connected between the neutral point and common ground, and this topology again does not require to assess the neutral point. This particular topology, but it adding one extra converter, interfacing converter for the AC supply. Nothing comes at free, as we know that we have to pay the price depending upon our requirement. Okay, so
Ankit, there are more questions in chat box. Can you please see and answer those?
okay. I'm where it is, sir.
Manish, chat box, do we have wind power generation over high-rise buildings anywhere in India?
सर वो इसका नहीं है.
That is not for you, right? So अंतिम पढ़ के बताओ कौन से
हाँ,
questions?
There is a question like how to select mode operation for CISO and MIMO mode.
TISO and MIMO mode. In for this particular one converter which I have shown for the solar boat, they are interested, I think, for that particular configuration. CISO and MIMO mode. Yes, I will show. This one. Okay. So CISO mode is the single input, dual output. So battery single input, dual output. There are two. One, I think I forget to discuss you. This one good question they have means he is asked. So CISO one, again there are two possibilities are there. PPV, when solar power generation is zero, so battery will supply to the load. Load means our whatever the motor drive system. If uh, the situation maybe their PPV power exactly, maybe this if, means CISO mode will come for the if a battery sorry, battery is fully charged. Okay, battery is fully charged, SOC is greater than 90%. So PV will supply power to the load. Okay, and MIMO means is asking about the this dual input, single output. No, MIMO case will not come here. Multi input, multi output system. Either it is a multi input, single output, single input, dual output. We can say CMO mode. Okay, like that, single input, dual output. So multi input coming PV to load and battery to load. Okay. So battery both are when P load is greater than PPV. So both are supplying. If you want to understand its operation, okay. So we can see here in a DSO mode. So DSO mode, a dual input, single output. Okay. So this is the switch S3. If battery is connected switch S3, if it is turned on, inductor will stores the energy. Okay, and okay, and switch S1, if switch S3 will be off, inductor will store energy through the PV. Okay, so it is the picture is coming for the dual input. Okay, and single output means if switch S1 is off. Okay, switch S1 is off, so situation will come that it will operate as a non-isolated shaping. There may be a possibility here in switch S3 and switch S1, depending upon the duty cycle of it. Mode, either mode second, this is the second, or this is the mode third will take place, depending upon the user I have shown here. If D1 is greater than D3, state 2 will take place. Okay, this. If D1 less than D3, okay, D1 less than D3, then this picture will come into this will come into the picture. Okay, so in this particular situation, we have to remember PV will not come into the may come not into the picture. Okay, because here one assumptions is there. If you want to understand its detailed operations in the paper, so battery voltage is higher than the PV this here the output. So this diode will be off. Because why it has been taken this situation? Because otherwise we have to two sources, only one source will be act one time, because two sources with different voltage cannot be connected in a parallel. Okay, so this is, if any other questions are there in chat box.
So there are no more questions.
No more question. So here DSO operations are there also. We have I can so with this one you can. This is the reference line, reference power line, and solar PV is not generating required amount of power. So battery in this battery is discharging, and solar PV is also supplying power to the load. The multi-input, we can say DSO means multi-input single output system. Here the important thing is that is this particular what I have told you already. Solar is on the roof, so it is the situation is that it may supply load as well as a battery. This is the important thing, this mode, which is not available in the conventional. We means even in except what I have told in electric vehicle on the which is running on the road. So some light electric vehicle e-rickshaw, we do not install the solar PV because the area is not that much, and so zero mode is usually not come. Okay. Any I think all the questions been from the participants answered. If you have any more questions and more anything you want to discuss with me, even maybe the question come in your mind, you can ask through the email also at the ankit@nsut.ac.in. You can mail it.
Thank you.
Okay. So this is all from my side, and if anything is still you want to discuss, you can mail it. Okay, thank you.
Thank you, sir. Thank you very much.
I can leave it.
Sir, that's it. Thank you, sir. Sir, session close कर दूं?
I'm sorry, I was not bothering